Welcome to lesson 5 of Year 2 Pure Mathematics Sequences and Series. Today we're going to look at sigma notation and how this can be used to describe a series. So we're going to get into this in some detail. Notice there's lots of new useful definitions here. We've got the binomial expansion again, so that's good revision. And we've also got the sum of an arithmetic series, the formula, which is provided for you in the formula booklet, and also the work we've just seen on the geometric series as well, including the sum to infinity. This is also provided in the formula booklet. So please pause the video and have a go at the warm-up questions. Okay, let's have a look at the solution to question 1. All right, so for question 1, I've just done part A already. We're just subbing in n equals 1, 2, and 3 into each of these series. Sorry, I beg your pardon, sequences. So the answers are highlighted. Please note, of course, especially in part 3, because we have 3 to the power n subtract 1 here, the n subtract 1, obviously, whichever term I'm in, if I'm in the first term, the power of n is 1 less. If I'm in the second term, it's 1 less, that's 1. And if I'm in the third term, the power of 3 is 1 less, which is 2. Okay, and I think those should be fairly straightforward. Now, let's have a look at part B. Here we're told to find the nth term for the following sequences. So for part I, let's see what's going on. Well, let's check. How are we getting from one term to the next? Well, it looks like we're multiplying by 3 in each case. Now, because it's a multiplicative relationship, we know that this is geometric. Okay? All right, so now we can write down some of the key properties. So we know what the first term is, that is 5, and we know the common ratio is going to be 3. So let's put those two ideas together. So the nth term rule is going to be 5 multiplied by 3 to the power n subtract 1, just using the formula that's provided. Okay, and then for part 2, let's see what's happening here. Well, it doesn't look like I can divide in this case to 11 by 8, 14 by 11. It's not going to give me nice numbers, and they're not going to be the same. So let's see, how are we changing? How are we getting from one term to the next if we're not multiplying by something? Well, it looks like we're adding 3, doesn't it? Okay, so this is arithmetic because it's an additive relationship. Okay, so for an arithmetic sequence, we know first term is A, and we have, if you remember, the common difference D, which in this case is 3. Okay, and we sub those two values into our general term for an arithmetic. So that's going to be A plus n minus 1 multiplied by D, just to remind you. So this is going to be 8. And then the D is 3, so I'm going to multiply the D by n subtract 1. Let's just expand that. So that's going to be 8 plus 3n subtract 3. In other words, this is going to be 5 add 3n. So that's our nth term rule. Okay, moving on to question 2. We're asked to find an expansion up to the x squared term. All right, now if we do that, we just need to rewrite this. So we know this is 1 subtract 3x to the power negative 1. And we saw this in the warm-up for the previous lesson. Okay, and then if you just identify what are the values of n, well, n is negative 1, and the b value is going to be negative 3x. So let's just make a note of those. So n equals negative 1, and my b is equal to negative 3x. Okay, and then we can substitute those into the binomial expansion given on the page above. Okay, so we're going to have this. So we're going to have 1 over 1 subtract 3x is going to be equal to 1 plus n times b, and then we only need one extra term, plus 1, beg your pardon, negative 1, multiplied by negative 1 subtract 1, which is negative 2, over 2 factorial, and that's going to be negative 3x all squared, plus some other stuff. Okay, remember the link between the equal sign. If I'm going to use the equal sign, I have to include the plus ... on the end. Okay, let's tidy this up now. So this is going to be 1 plus 3x, and then lots of cancellation. We have a negative term squared, that's going to be positive, and 2 negatives make a positive, and the 2's cancel, that's going to be plus 9x squared, plus some more terms. Now, you'll notice that this is a series. Okay, we'll talk more about the series in a minute. Now, we could actually find the sum to infinity of this series. In fact, that's the next question. So how would we do that? If we were confronted with what looks like an infinite polynomial expansion, how do we find the sum to infinity? Well, in exactly the same way as we found the sum to infinity, or how you find R and A for this. Oh, excuse me, just making a mess of this. Let me start that again. So it would be exactly the same as finding R and A for this geometric sequence over here. So what is the link between each of these consecutive terms that we're adding? Well, you'll notice to get from one term to the next, well, I've multiplied by 3x there, haven't I? Okay, it's definitely not arithmetic because I can't add 3x to the next term and I'm not going to get the 6x. I've got 9x squared. But if I multiply by 3x, I get 9x squared. So I'm clearly multiplying by 3x in each case. Okay, now we'll have to assume that the 3x, remember, is between negative 1 and 1 for this to be true. Okay, but just for you to bear that in mind. All right, so let's do it. So we now know what A is. Well, we already knew what A is. It's 1. It's the first term. Okay, and the common ratio we can see is 3x. And we know that the sum to infinity is A over 1 subtract R, which is 1 over 1 subtract 3x. And we get exactly the same as what we saw in the previous part of the question. So it all fits together really nicely. Okay, moving on to question 3, we have to find the sum of n terms of this series. Well, there's two ways of looking at this. We could say, all right, well, what actually is going on here? Is this a arithmetic sequence or series, I beg your pardon, or is it a geometric series? Well, okay, if this was geometric, so let's consider the geometric option. What information do we have? Well, we have A, which is obviously 1. And what would the common ratio be? What we're multiplying by each time to get from one term to the next? What is the link? Well, we'd have to be multiplying by 1, wouldn't we? Okay, that's the only way, multiply by 1. It's the only way this is going to work. Now, if we put that in, if we put in R equals 1, you're going to notice we're going to run into a problem, because if I write out the sum of n terms, remember it's A multiplied by 1 minus R to the n over 1 subtract R. And this is where we have the problem. If we sub in R into here, and R is 1, we're going to get 0. Okay, this would equal 0. So we're not allowed to do that. So this cannot be a geometric series. So we've got to consider now the arithmetic option. So let's do that. So we'll just partition that off. So the arithmetic option, or way to look at it, I should say, is going to be the following. So we know A is going to be the same. That's going to be 1. And we'll just erase this. let's look at it a different way. Well, we're going to be adding 0, aren't we? We're not actually changing the terms whatsoever if we consider this as an arithmetic series. So we're just going to be adding 0 and adding 0 again. So my common difference is just 0. So let's do the sum of n terms. So we're going to need the arithmetic version of this. So the sum of n terms is just going to be, let's undo that, n over 2 multiplied by 2a plus n subtract 1 multiplied by d. Now then, just to make this a little bit shorter, if d is 0, as we can see here, that's just going to kill this term here, isn't it? There isn't going to be an n minus 1d if we sub that in. So that's just going to leave us with this. We're just going to be left with n over 2 multiplied by 2a. Okay, now the a is 1, of course, so let me just undo that. We can just change that to 2. Okay, and then if we just cancel out the 2's, this is just going to give us n. All right, so the answer to that one, the sum of n terms of 1 n times is pretty obviously just going to be n, because you're going to have n lots of 1, aren't you? Okay, I think that's pretty obvious. If you're not sure what I'm talking about, just let me show you a slightly different way. So if I just did 1 plus 1 plus 1, that's 1 multiplied by 3, isn't it? So it's just going to be 3. So if I do 1 plus 1 plus 1 n times, that's going to give me n. So for part B, we have to find the sum of the first n natural numbers. Okay, this is always a nice little proof we can do. So the first n natural numbers, so this would be 1 plus 2 plus 3 plus 4, and so on and so on. And apparently, it's equal to that. Well, my first term is a, of course, and my common difference, okay, this is an arithmetic series, isn't it? We're adding each time. We're just adding 1. So a is 1 and d is 1. So let's substitute those into the sum of n terms formula, which we proved in that lesson on arithmetic series. That's 2a plus n subtract 1d. Let's sub in our values. So we're going to replace a with 1 and d with 1 also. Let's do that. So this is going to be n over 2, which appears in the final answer, so that's probably going to stay. And then we've got 2 lots of a, so that's just going to be 2 plus, and d is 1, so it's just going to be plus n subtract 1. Now, we can collect like terms inside the bracket here. Okay, we've just got 2 subtract 1 there. So that's going to give us our final answer. So it just pops out really nicely. So we get n over 2 multiplied by 1 plus n. And it's just written in a slightly different way. So i.e. n over 2 multiplied by n plus 1. Okay, so that's the sum of the first n natural numbers. Okay, moving on to question 4. We're going to use these results from question 3, okay, to find the sum of n terms of the following series. All right, well, remember the result from part A. We know that if we take 1 plus 1 plus 1 plus some more terms, we're going to get n if we're summing over n terms. So there'll be maybe a plus 1 there as well, just for the nth term. Okay, can we use that? Well, yes, we can. This is going to be equal to, I can factor a 3 out of all of these. So this is going to be 3 multiplied by 1 plus 1 plus 1 plus, and the rest. Okay, and we'll close that. And we know that answer, don't we? So this is just going to be 3 multiplied by n. because it's the result here. Okay, so that's 3n. Might have been obvious, but I just wanted to use that result from the previous question. And finally, we've got what looks like the 4 times table. Now, if it's the 4 times table, what we can do is we can factor out 4. And if we do that, we'll be left with 1 plus 2 plus 3 and so on inside the bracket. Now, these look like the natural numbers, don't they? In fact, they are the natural numbers. And we have a result for this. It's here. We've just proved it. So I can replace 1 plus 2 plus 3, etc. with n over 2 multiplied by n plus 1. Let's do that. So this is going to equal 4 multiplied by n over 2 multiplied by n plus 1. Close that. Okay, and then the 2 will cancel in the denominator. So this is going to go here. So 2 and 4. That's going to cancel it down to 2. And that's going to be 1. So the answer is just going to be 2n multiplied by n plus 1. And you could actually check this if you wanted to. If you wanted to check the formula, just sum the 4 times table over however many terms you like. Okay, and we'll stop that there. So let's have a look at what sigma notation actually is. Sigma is a Greek letter. We're using the capital version in this case. And in mathematics, we use it to signify what we call a summation. And you'll know what a summation is. We've talked about this word before. You know, it just means we just need to add up. Okay, that's all it means. To sum something, it just means to add it up. Now, if you look at the example below, this is the way we use it. So we're summing using the capital sigma. That's what that symbol means, as we just said. So here, so that's telling us what to do. And then we have limits, as we saw in integration. We have a lower limit, r is 1, and an upper limit, which would stand for r equals 4. Now, the easiest way to explain this would be just to write out what's actually going on here. So what I'm going to do, I'm just going to write out the sequence by substituting in these r values. And remember, r would be a natural number because we're talking about terms of a sequence. So let's start off. So if we have r equals 1, then our expression here tells us that we have to multiply r by 3 and add 5. So we have 3 times 1 add 5, which would give us 8. Okay, now that would be the first term of the sequence. Okay, I'm using the word sequence here. I'm going to use the word sequence and series interchangeably, but we're just going to talk about the sequence itself first. Then r is 2. We have 3 multiplied by 2, and then we add 5. Okay, so that's going to give us 11. You can see the substitution there. I mean, you've done this so many times now. It shouldn't be a main issue, but I'm just going to highlight it anyway. So that's where I'm summing in the 1. That's where I'm summing in the 2 into the expression 3r plus 5. So let's just do the rest of it. So we now have r equals 3. So we have 3 multiplied by 3, and then we add 5. Okay, so that's going to give us 14. And finally, we have r equals 4. So we have 3 multiplied by 4, add 5, which gives us 17. So we've now generated our sequence, and you can see the links here. We are clearly generating an arithmetic sequence. And you can see this because we're adding 3 every single time. Okay. So what is this rule telling us? Well, it appears to be telling us the nth term rule, doesn't it? Yeah. So if I take the rth term rule, in fact, because we're using letter r. So if you can imagine that we're increasing each term by 3, and then the term, the constant that you would add on would obviously be the 5, because you have this plus 3 from term 0, if you like, before the first term. Anyway, that's just revision. So we've generated the sequence. Now, what that means is, as I started to write out, I could write out the sequence over here. So we have 8, 11, 14, and 17. Right, so we've written out the sequence, but what we're supposed to do with it, well, this is what the summation tells us. We add them up, don't we? Okay, so let's add them up. Okay, and that will give you an answer of 50. Right, so that's what it means in longhand, as in we've written out the entire summation. For the R values, going from 1 up to 4, it means I've taken all the natural numbers from 1 to 4, or in other words, term 1 up to and including term 4. So that's what those limits mean. Very, very similar to integration, in fact. Before we progress on to the worked examples, I just want to go over 2 of the useful results that we've already met. If I sum from 1 to n, just the number 1, remember what we've just said. We're adding up the sequence. Now, every term of the sequence is just 1, okay? And adding them up makes it into a series. But we're adding 1 to itself n times. So it's the nth term of the 1 times table, if you like. So this is going to just be n. And you prove this in the warm-up. And then the other result that we found was the sum of the first n natural numbers. And you can see it's denoted by the sum r, from r equals 1 up to n. So I've just replaced r with 1, 2, 3, 4, etc. And then the summation tells me I've got to add them together. And we found, again in the warm-up, that we get this result here. So those are 2 very important results that we might be able to utilize at some point during this lesson. Now, for worked example 1a, we're asked to sum 4r plus 1 from 1 to 20. So those are our lower and upper limits. Now, what I've done is I've just written out the first 3 terms of the series, just so we can see what's going on. So when I sub in r equals 1, oops, I didn't want to do that. When I sub in r equals 1, of course, I get 5, which is the first term of the series. So this is the value of a, isn't it? The first term. Just make a note of that. That might be useful. So 5 is our first term. When I sub in r equals 2, I get 9. Now, this is again useful because this is going to tell us the common difference, isn't it? And I've just done the third term, subbing in r equals 3, which gives us 13, just to make sure that it is obviously an arithmetic sequence. I mean, of course it is, but there's no harm in checking that. So we're clearly increasing by 4 every single time. So 5 plus 4 is 9, plus 4 is 13. So we've got some continuation dots here. Now, the reason why is I don't want to have to write out the entire sequence and find the sum of the series explicitly by writing out all 20 terms and adding them together. That wouldn't be a good use of time. What I can do, though, is I can quickly find out what the last term is. Now, we're summing the first 20. So if I write in r equals 20 here, we're going to have 4 multiplied by 20. And then if I add 1 to it, that's going to give me 81. Now, this is very handy information indeed. I'm just going to make a note of this. This is the last term. And if you remember, we called the last term L. So this is the last term. Right. Now I've got everything I need. So let's just summarize what we've got. We have A, which is, of course, 5. We have our common difference, which is 4. And we have our last term, which is 81. Now then, recall formula for the sum of n terms. There was two variants of this. There was the standard variant where we sub in a, d, and n, and then there was another variant where we can use the last term. So I'm just going to have to remember to write down that n is 20. We're summing over the first 20 terms here. So the sum of n terms we can also write as n over 2 multiplied by a plus l inside the brackets. Okay, just recall that. Now we can perform our summation. So we're going to sum the first 20 terms. So this is going to equal 20 over 2 multiplied by 5 added to the last term, which is 81. So in other words, this is going to be 10 multiplied by 86, which is, of course, 860. You can check this on a spreadsheet if you like, if you can do this on Excel pretty easily. But I think that will do nicely. Right, for 1b, again, I've just written out the first 3 terms of this sequence, which we're going to sum as a series. So when r is 1, we get 2. So that's our first term. Just make a note of that. So this is our a. When r is 2, we sub that in, we get 6. Okay. And then when r is 2, you get 6. When r is 3, you get 18. You can probably tell by the nth term rule here, well, it's the rth term rule, isn't it, that this is going to be a geometric sequence. And we can verify that by checking the common ratio. So clearly, as I'm moving from 2 to 6, I'm going to be multiplying by 3. And as I move from 6 to 18, I'm also going to be multiplying by 3. So let's make a note of everything we know so far. So we have the first 3 terms, and that's going to give us a and r. So we'll summarize that. So a is going to be 2, and the common ratio r is 3. And we also know that we're going to sum over 8 terms. So n equals 8. Right, now we can go straight to the sum of n terms formula for a geometric series. So Sn is going to be a multiplied by r to the n subtract 1 over r subtract 1. Now I'm just going to leave a note here. Note. Because r, this value, is greater than 1, okay, we're going to use what I'll call the r minus 1 version. Remember, there are 2 versions of this. All right, just to be aware of that in case you're wondering why I've chosen that form. Let's sub everything in. So S8 is going to equal a, so that's going to be 2. Multiplied by 3 to the power 8, subtract 1, divided by 3, subtract 1. Well, that's going to be 2, so we're going to get some cancellation here. So 2 over 2 is just going to be 1, so this is going to just be 3 to the power 8, subtract 1. Now, okay, so we just need to evaluate this. So let's get our calculator. Right, so I've just got enough space here, I think. So let's have a look. So 3 to the power 8, just come out of that, subtract 1, and what do we get? 6560. Example 2, 2a, in fact, we're going to evaluate a summation, and I want you to just pay close attention to this because this is very important. Please notice the lower limit of the sum starts with r equals 5. So we're evaluating from the 5th value, I beg your pardon, the 5th term of this series, going up to the 12th term of the series. Now, what I've done, just to sort of emphasize the point I'm trying to make, the 5th term of the series, is our first term essentially, and the 12th term of the series is essentially our 8th term. And you can see that because if the 5th term is now going to be the first term that we're evaluating, there must be 8 terms in this series, because the natural numbers 5, 6, 7, 8, 9, 10, 11, 12, there are 8 of them. Now, this is important because if you were asked to evaluate this summation, you might be thinking, well, how many terms am I going to sum over if I'm going from r equals 5 to r equals 12? Well, you might think, well, the n value would just be 12 subtract 5 if we're going from r equals 5 to r equals 12. Now, that would give us 7, okay, which is 1 less, because remember, of course, the r equals 5 has to be counted also. So we need to add 1. That's really, really important that we remember this. So we're going to add an extra 1 to accommodate for the fact that we are starting at the 5 and finishing at 12. So that will give us the 8 terms that we need to sum over. Okay, so that's our n for this summation. We're going to sum the first 8 terms. Now we're going to find out what the first couple of terms are so we can figure out what a and r are going to be. So if I sub in r equals 5, which is where we're beginning, we're going to have 2, beg your pardon, not 2, just undo that, 3 multiplied by 2 to the power 5 subtract 1, okay, which is 3 multiplied by 2 to the power 4. Okay, now that's going to give us 48. So the first term in this geometric series is 48. Now let's sub in r equals 6. So now we're going to get 3 multiplied by 2 to the power 6 subtract 1, which is 3 multiplied by 2 to the power 5. And as you can see, we're simply multiplying by an extra factor of 2 here. So that's going to give us 96. All right. And obviously r equals 7. If we sub that in, that's going to be 2 greater. We don't need to carry on with that. That's going to be 2 lots of 96, which is 192. So let's fill in what we know. So we can see the multiplicative factor is 2, okay, going from one term to the next. My first term is 48. So I can write down this information now. So we know that the first term of this series is 48. Okay, and the common ratio is 2. And from what we explained earlier, 8 is the number of terms we're going to be summing over. So we need to write that down also. So n is equal to 8. So now we need to do the summation. So the sum of the first 8 terms is going to equal a, which is 48, multiplied by r to the power n. So that's 2 to the power 8 subtract 1 divided by r subtract 1. And remember, the r value here is greater than 1. So that's a reminder, of course, that we have to use the r minus 1 form of the summation formula. Okay, we mentioned that earlier. So let's carry on with this. So this is going to be 48 multiplied by 2 to the power 8 subtract 1. And we just need to evaluate this. So let's get our calculator. Let's move it over. Yeah. So 48. Oh, got to click on the mouse option. So 48 multiplied by, open a bracket, 2 to the power 8, just come out of that, subtract 1, close your bracket, and we get 12,240. Okay, so that's good. So we can fill that in. So this is 12,240. Okay, and there we go. Now, 2b is actually quite interesting. This has come up on a previous exam, and I think it's been published in the examination material on the launch of the course in 2017. It's a tricky question because we have three components to this summation, or three terms, if you like. So we've got the 2 to the power r, and the negative r. Now, there's a really nice property of summations which I'm going to use now. When you do the summation of a sum, or some linear combination of terms like this, you can actually separate them out into three separate summations. So what I mean is, I'm going to write it out and show you what I mean. So I can write this as the sum from r equals 1 to 8 of 3 plus the sum from r equals 1 to 8 of 2 to the power r, and then I have to subtract the sum from r equals 1 to 8 of r. Okay, so we can deal with these three summations separately, and that's what I'm going to do. So I'm going to call this summation 1, this one 2, and this one 3, and then we can compile our answers later. The reason is because they're very different. We have a linear, what we would call an arithmetic series, and we've also got a geometric series built in. But because it's a linear combination of those, we can separate them out into three summations. So let's look at part 1. Now, the sum of 3 for over 8 terms. So now just remember what we said earlier. We actually dealt with this in the starter activity. What I can also do, if I have a common factor in my collection of terms that I'm summing over, if there's a common factor, I can actually factor it outside of the sum. So I can actually write it like this, where I bring the 3 out. And that means I'm going to be summing 1 8 times. Okay? And we saw this earlier, okay? So it's 3 multiplied by 1 plus 1 plus 1, and that's done 8 times. So all this means it's just 3 times 8. Which is, of course, 24. So that's the first bit. Remember, we saw that the sum, just a reminder from earlier, the sum for r equals 1 to n of 1 is just whatever the n value is. Okay? Because you're just adding 1 to itself n times, so you're always going to get n. So that's that one. Now, we're going to look at summation number 2 now. So number 2. Now, this one looks like a geometric series. So we can deal with this one as we've dealt with previous geometric series. So if I take the summation here, from what r equals 1 to 8 of 2 to the power r, and let's just look at the first few terms here. Well, this is going to be 2 to the power 1 plus 2 to the power 2 plus all the way up to 2 to the power 8. So you could actually work this out longhand if you wanted to, but we can use the summation formula as well. So if we use the summation formula, let's just write down what we know. Well, we know that A is, of course, just going to be 2. Our common ratio, well, if you're going from what is 2 to 2 squared, which is what we've got here. I don't know why I wrote that out twice. 2, which is 4. Obviously, you're multiplying by 2 here. Okay? And you're multiplying by 2 again to get 2 cubed. So your common ratio is, of course, 2. And we're summing over n terms. So n is going to be 8. So let's put all that into a summation formula. So the sum of 8 terms is going to be A, and r is greater than 1, so we're going to use the r minus 1 version. 2 to the power 8, subtract 1 over r minus 1, which is, of course, 2 minus 1. So this is just going to be 2 multiplied by 2 to the power 8, subtract 1. Okay, now let me just work that out. Let's get the calculator. Okay, I'm just going to erase some of this stuff. Okay, so this is going to be 2 multiplied by, open brackets, 2 to the power 8. Come out of that, subtract 1, close your bracket, and this is going to be 510. Okay, great. So let's write that in. So 510. So that's part 2 done. Good stuff. And then for part 3, this is another result we saw in the warm-up. I beg your pardon. Well, yes, in the warm-up and slightly later. It's the sum of r, which is the first, well, in this case, the first 8 natural numbers. So we're summing from r equals 1 to 8 of r. Now, if you just write those out, r is 1, r is 2, etc., plus 8. And you can just add those together. It won't take you long if you wanted to do that. But imagine if this was 800 and not 8. That wouldn't be a practical way of doing it. So let's use that formula that we derived. So if you remember from earlier, the formula we found was that the sum for r equals 1 to n of r is just n multiplied by n plus 1 over 2. Okay, so we can use that result. And I'll just get rid of that because it's just a bit in the way, isn't it? So we'll just finish this off. So this is going to be n, which is, of course, 8, multiplied by n plus 1, which is, of course, 9, divided by 2, which is 4, multiplied by 9, which is 36. Right, so those are the 3 summations done separately. Now, we've got to be careful here. If you just go back to the start and just check what's going on here. We had the first summation, which we've done, okay? And then we're adding the second summation. So we're going to add 1 and 2 together, our results. So it's going to be this result here added to this result here. And then we have to subtract our final result, which is 36. So we're going to subtract the 36. So the final sum is going to equal the sum of 3, which is 24, add 510, and then subtract 36. So in other words, that's just check that. Sorry, that's 510, isn't it? Beg your pardon, 498. Okay, just want to double check that. So yeah, 24 subtract 36. Yeah, does that seem reasonable? Yes, I think it does. So there's our final answer. And for worked example 3, which is our final example today, we have a show that. So we're supposed to create this quadratic from a given summation here. Right, let's have a look how to do this. Well, we're going to use the techniques that we've looked at already. So just on first inspection, this appears to be an arithmetic series, an arithmetic sequence that we're going to sum as a series. And we're given the total as 623. All right. Well, let's write a few of the terms out and see if we can deduce the first term and the common difference. So when r equals 1, we're going to have 5 multiplied by 1 plus 7, which is going to give us 12. Okay, so that's our first term. And if we do the second term, just to get that common difference, we have 5 multiplied by 2, then add 7, which is, of course, 17. I mean, you don't need to do that. I mean, it's pretty obvious from our two results here. You're going to get, you've got a difference of 5, and it also says 5 here. I'm just trying to be thorough here. Okay, so it all kind of ties together. So we're adding 5, aren't we? And then this term here is, of course, your A. Let's write these down. So we have A is equal to 12, and our common difference D is equal to 5. And we also know that we're summing the first K terms. So over the first K natural numbers, we're going from 1. So always make sure you check that. That's really important, that you're starting at 1, because we saw a different version of this when we did example 2A, where it didn't start at 1. So we're going from 1 to K. So we know that's K natural numbers there. So that's our n value. So our n value, we're going to sum over K terms. And we actually know that the sum of those K terms is 623. So we've got all this information, and we can plug all this into the arithmetic series formula. So remember, the formula is the sum of n terms, given to you in the formula booklet, of course, equals n over 2 multiplied by 2a added to n subtract 1 multiplied by d. We'll close that off. That's what we're going to use. Now, in this case, we know that the sum of K terms, which I'll just put in parentheses like that, because it's actually given a value. So we actually know what this is. That's going to be n over 2. So this is K over 2 in this case, multiplied by 2a. So that's 2 multiplied by 12. Added to K subtract 1 multiplied by d, which is 5. And we know the answer is going to be 623. Let's tidy this up now. K over 2. Okay, and that's going to be 24. Added to multiply 3 by 5, 5k, subtract 5, close your brackets, equal to 623. Okay, I'm going to multiply by 2 and just do a little bit more tidying up inside the square brackets. So we're going to have k, and then with 24 subtract 5, that's obviously 19, added to 5k, and I'm going to have to double both sides, so I've got to double 623, which is, of course, 1246. And you can see that number in the quadratic already, so this looks like we're on the right track here. Okay, multiply 3 by k, so we're going to have 19k added to 5k squared. Subtract 1246 is equal to 0. And we've essentially got the right answer. I'll just rearrange it. So therefore, 5k squared added to 19k, subtract 1246 equals 0, as required. Okay, so that looks great. So we seem to have been successful here. Now, I've got the calculator out, as you can see. We're going to have to find the value of k. So that was all part A, and I'm not very good at writing down which part of the question we're doing, so I apologize for that. That's A. Now for part B, let's use our calculator. You can do this by factorization, of course, so we'll go back to the menu. We're going to solve an equation, so I'll just select that. Solving a polynomial, degree 2, it's a quadratic. And we just plug in our A, B, and our C. So A is, of course, 5. Okay, our B is 19. And our C is negative 1, 2, 4, 6. Okay, there we go. Right, so we have two results. So, oops. back to that. Sorry, beg your pardon. So K1 is 14. And what's the other solution? Negative 89 over 5. I'll just write that down anyway. It's not going to be right, is it? Okay, so I've alluded to the fact that this isn't going to work, this K2 one, simply because K must be a natural number, and that is not a natural number. It's a fraction and it's negative, so it fails on 2 counts there. So the first result is going to be our answer. So from ClassWiz, where we had A equals 5, B equals 19, and C equals negative 1, 1, 2, 4, 6. We got K is equal to 14. Okay, and that's the answer. So that concludes the lesson.